Good afternoon.
Good afternoon.
All right, so how's everyone today?
Good.
Good to hear. So let's see, we've got everybody in Winslow. Is everyone at Mogollon? Or are we missing one?
Yeah.
Okay.
No, everyone's here.
Everyone's there? How about St. John's? I don't see anybody.
We're missing David right now.
Oh, okay. All right. Well, let me know if he comes in, okay? And then I don't. And let me. Yeah, there. Your camera's a little bit better. That helped. Oh, I can see you guys now. Okay. Yeah, that's better. That's better. Thank you. But yeah, let me know if David comes in. All right. So, did anyone do anything amazing over the weekend? Nothing amazing? Let's see, I did go to the Standing on the Corner Festival for the first time in Winslow.
How was that?
It was a lot more crowded than I thought it was. So anyway, and is Miss Lopez there?
She's out of the room right now, but she's here.
Oh. Yeah, so you can tell her that I took my family to Relic Road.
Oh.
That's never fails to please. So that's pretty awesome. I also went to my very first Christian rock concert, and that was just crazy. I never seen anything like that before. But any of you heard of Jordan Felice? No? Anyway, totally legit performer. So anyway, I mean, I've been to rock concerts before, but it was a little different. So, but I enjoyed it. Anybody else? Do anything amazing?
Hannah backed into a ditch.
I don't want to talk about it.
With your own car?
Yeah.
Any
It was a truck, though, but so it got out nice and easy.
Any permanent damage?
Nope. Thank goodness.
Just her dignity.
Yeah.
Just your pride, huh?
Yeah, exactly.
Well, I was at Walmart in Payson, and somebody did a hit and run on my car. So that was totally uncool because it's probably over $1,000 of damage. So anyway, yeah. So what?
David's here.
Yeah, I'm here.
Oh, okay. Thank you. All right. All right. So anything else? Anybody else do anything? All right. Well, okay. So let me tell you what our plan is for today. What we want to do is we've just got a little bit to do in 2.5, and we'll knock that out and then start in on 2.6. 2.6 is at least a 2-day lesson, so we definitely want to get started on that. So, all right. So we were on practice 10, and so let's kind of go through this. Okay, so this says, let me switch okay, so this says to show that there is a root of the equation between y equals x cubed minus 3x minus 1 between -1 and 0. Okay, so does anyone remember what we have to do here? All right, go ahead.
You just have to see if there's a sign change between the two values when you put those numbers in.
Right. And you actually do have to state that this is a continuous function so that there's no jump. So you want to say, okay, first of all, the function's continuous. All right. And then you want to see if there's a sign change. So plug in -1 for x, and then plug in 0 for x, and see if you get a sign change. All right, so Nathan, when you plug in -1 for x, what do you get?
So that's -1 minus 1.
Okay. All right, and when you plug in 0, what do you get?
-1.
-1. Okay, so there we have a sign change. So since the function is continuous and you have a sign change, then somewhere the y value has to cross the x-axis. It has to be equal to 0. And so that's it. So by the intermediate value theorem, so IVT, there must be a root between -1 and 0. Okay, so that's actually a calculus proof. I know it doesn't seem like the proofs you do in geometry, statements and reasons or whatever. And really in higher level math, you kind of don't do those kind of proofs anymore. I mean, they're good to teach logic, but you just sort of explain your reasoning here. Okay. So any questions on that? So when you're asked to show that there's a root, there's other ways that we can ask that same type of problem. Okay, so these are 4 equivalent statements to say that A is a 0 or a root of f, A is a solution of the equation, A is an x-intercept of the graph, or x minus A is a factor of f. So if you're asked to prove any of those, you do the same thing. You use the intermediate value theorem. Okay. Anybody need more time on that? Okay. Okay, so similarly, we can use the intermediate value theorem to show that, like, for example, these two curves intersect. Okay. So if they're going to intersect, then that means you can set them equal to each other. Okay. All right. And so then think about how we would solve this. So you can go through and solve and do the intersection and say, okay, so to get rid of the radical, square both sides. And then square this out. And then you can go through the steps to actually solving it. Okay. Now, let's go. Now, if you're going to do it on the calculator, see the calculator, what it does is when you do second calc intersect, what it does is it looks for, it's like the common x value that would be on both curves that would set the y's equal to each other. And so it's sort of a version of the intermediate value theorem. Okay? So when we do second calc, here, let me pop up the calculator real quick. So there's actually the last time we talked about when you do finding zeros, the calculator is looking for a sign change. So like second calc 0, the calculator actually uses the intermediate value theorem. All right, let me just, come on. And when you do intersections, it kind of does something similar. Okay, so let me just show you. If you just like, if you let's see, x squared, and let's say we were looking for x minus 2. Okay, so that doesn't have an intersection. So let's change it to x plus 2. So basically what we're doing here is when we do second calc intersect, it's like it's setting those two equations equal to each other and looking for the common y value. So if you do first curve, enter, and see it actually intersects twice. So if you just press enter, it'll just find one of them. If you want the other one, you kind of go towards the other one. Okay. Now let's go back to. Okay. So if we want to use the calculator to find the intermediate value theorem, we're going to put each of those values in the calculator and try to find the intersection. Okay. If we're trying to do it algebraically without the calculator, what we want to do is show that somewhere that that the y value here is going to change from one side of 1 to the other side of 1. So here, if x equals 0, this is equal to 0. If x is equal to 2, then this is equal to 2. So if the y value goes from 0 to 2, then somewhere in between, it has to hit 1. So that's kind of the logic here with the intermediate value theorem. And it only is true because the functions are continuous. So that means it has to take on every value in between. Okay? Now, going back to, let me go back to show you something else on the calculator. Maybe you can be writing that down, but we'll move this over. Okay. Okay, so with the intermediate value theorem, so the calculator is, when it's trying to find a 0, it's looking for where the y values change from positive to negative or negative to positive. So let's say if I do second calc 0, okay? This time I'm going to try to find this positive 0 right there, okay? So I'm to the left of it, so let's press enter. Now, I'm supposed to go to the right of it. See, the y values are supposed to change from positive to negative. If I were to press enter there, see, then what's happening is it's saying no sign change. See, it's looking, because of the intermediate value theorem, it's looking for one y value, the y value to go from negative to positive. So if that doesn't happen, then it gives you an error message and says, oh, there's no 0 here. Okay? There's no sign change. So if both of your y values are positive or both of them are negative, then the calculator can't find the 0 in between. Okay? It's because it's looking for the sign change. Okay? Now, on this example, why are we not, I mean, we didn't get a sign change. Why is this one okay? And the practice of 10 would not be okay. See, we got a y value here of 0 and a y value here of 2. The sign didn't change. Why is that okay?
Because the line that you're wanting it to intersect is equal to 1, not
Yes.
0.
Exactly. So you're wanting it to cross 1. Now, if you want it to cross 0 every time, then what you can do is actually subtract the 1 from each side and have it set equal to 0. And then you find one x value that's positive and one that's negative. And then that would prove that you would have a 0. Okay? All right. I hope that's not too abstract, but any questions on that? Okay.
Wait,
Go ahead.
actually, so when it's asking to just prove it, we don't have to find the specific value that they do cross. We just have to find that they do cross,
Yeah,
right?
you're just proving that it has a solution.
Okay.
So that the solution exists. Okay? So if whatever this number is, you want to get one y value on either side of it. Okay? All right. Now, the last little part here is actually a very important idea. Okay? Doesn't look like much on the student success organizer here, but it's actually a pretty important idea. What's called a continuous extension to a point. Okay? So remember that one of the discontinuities is called removable. Okay? That's where you have a hole. So we can remove a discontinuity from a graph by redefining the function. And we redefine the function in such a way that we plug the hole. So it's kind of a weird idea, but plug in the hole removes the discontinuity. It makes it so that it's a continuous function. Okay? So what we have to do is figure out what's the y value there and what's the x value there. And then we define that x value to be that y value. Okay? So let me give you an example here. All right. So we know that the limit of sine x over x is equal to 1. That limit. But the problem, so this is not continuous though. Sine x over x is not continuous at x equals 0 because at x equals 0 the function is not defined. So at x equals 0 there's a hole in the graph. So what we do is we take this function and we give what's called the continuous extension and say, okay, this is only defined for x not equal to 0. At x equals 0, we're going to define the function to be 1. And so what that does, this highlighted part here, plugs the hole. So we figure out where the hole is in the graph, and then we define the function so that that point is defined, and that plugs the hole. And so now this blue curve is continuous. Okay? There's no hole. Okay, so let's go back to this one. Okay, so you remember that what causes the hole is when you factor and cancel. So this would have a hole at x equals 2 and at x equals negative 2. So there would be two holes to fill. And so then we say, okay, otherwise when we cancel, this is equal to y equals x plus 3, except for the two holes. So then what would the y values be? Well, at x equals 2, 2 plus 3 is 5. So we say at x equals 2, the function is equal to 5. At negative 2, we get 1. So these are the continuous extensions that fill the holes. And so now, this function is continuous, whereas this one is not. All right? So let's see if you understand what I'm saying here. All right, so go ahead and try practice 12. So what point would you need to fill the hole? All right, so Denon, when you've got it. Or if you're stuck, let me know.
-4 at x equals -2.
Okay? So at x equals -2, you would want to define the function to be -4. That's exactly right. Okay? So let's just go through it. So when you factor and cancel, then you can see that you would have a hole at x equals -2. So that gives you this part right here. So then to figure out what this is, then you imagine, okay, if you did cancel those and you put in -2 for x, -2 minus 2 would be 4. And so that is the removable discontinuity. So we just filled the hole with that point, -2, -4. Okay? And so now this function, this original function is going to have the same graph as y equals x plus 2. There's not going to be a hole there. All right? So that's an important idea, to fill the hole of the removable discontinuity. Okay, any questions on that? All right, so I think that pretty much every quiz I've ever seen on this section, or even every test on chapter 2, will have something about a removable discontinuity. Okay, so the idea of getting rid of that hole. Okay, so that's it for 2.5. Were there any other questions? Anything that you missed? Any of the practice problems you'd like me to go over in 2.5?
I just have a question.
Sure.
Are we just gonna do 2.4 quiz on Wednesday?
So no, we'll do 2.4 and 2.5.
Okay.
So come with questions tomorrow if you have any other questions on 2.5. But we'll have the quizzes 2.4 and 2.5 on Wednesday. Okay. All right, anything else?
What is the test for this chapter going to be?
So all we have left is 2:6 for chapter 2. So I'm thinking that well, let's see. I can't remember. Did we say we could do one quiz in the test, or no, just the test? I can't remember what we decided.
Just the test.
Just the test.
Yeah.
Okay. So then what we would need to do is, because we won't be ready to do the 2-6 quiz on Wednesday, even if we finish it tomorrow. So what that means is that it will actually be then 2 weeks from Wednesday is when we take the test on chapter 2. So I'll give you some time to go over some practice problems and ask me questions and whatever you need. Okay? All right. So let's go ahead and move on to 6. All right, so 2-6 is on limits involving infinity and asymptotes of graphs. So this is the first part is similar to finding a horizontal asymptote in pre-calculus. And then this last part about asymptotes, we talk about vertical and horizontal asymptotes. And so this last part of this section really is pre-calculus, okay? But there's just a lot in this section. They used to have it separated into 2 sections. And I kind of like that better, but it is what it is. All right, so first of all, we're going to be talking about limits where our answers are infinity or negative infinity. And so those are infinite limits. But infinite limits are not limits that we've learned previously. So if we had a limit and the answer was 5 or something, that's a specific value, okay? Infinite limits prove useful symbols and language for describing the behavior of functions whose values become arbitrarily large, whether positive or negative. And I've lost the board. Okay. All right, let's try this. Okay. Okay, so if we write that a limit equals infinity or negative infinity, we are not saying the limit exists. Okay? It's better to say the limit goes up to infinity or down to negative infinity versus the limit doesn't exist at all. It's just giving more information. Okay? So it's still the limit doesn't exist, but if it goes all the way to infinity or toward negative infinity, that's a little more information. And so we like that answer better. Okay, so for example, if this is the graph here in blue of y equals 1 over x. All right, so to determine whether the limit exists as x approaches 0, we look at the left and the right hand limits. So as x approaches 0 from the left, the y values get more and more negative. So we would say the limit as x approaches 0 from the left is negative infinity. All right, then as we look for values as x approaches 0 from the right, the y values get bigger and bigger as x approaches 0 from the right. And so we would say that limit is positive infinity. But since these don't match up, then we would say the limit in general, since those are not equal, does not exist. Now, we could do this without the graph. You can just imagine, okay, so as x approaches 0 from the left, so you could even use your calculator and say, okay, so that would be like negative 0.1, negative 0.01, negative 0.001. Or from here, 0.1, 0.01, 0.001. And as the denominator gets smaller and smaller, then 1 over that becomes larger and larger. And so you can see that these don't match up. So the limit as x approaches a of any constant, it doesn't matter how big the constant is. If the denominator is going to go to 0, then your answer is going to be either positive infinity or negative infinity. You don't put plus or minus infinity. It's going to be one or the other. And so it really just depends on what the constant is. Okay? And if this is going to approach 0 from the left or the right. So you look at the signs. Okay? So let's see if you can, so as x approaches 1 from the left, so you imagine, like, say, 0.9. Well, 0.9 minus 1 is negative, so you have a constant over 0, but this is going to be negative numbers, so this is going to go to negative infinity. All right, well, as x approaches 1 from the right, see, this is still going to be a constant over 0, so the answer is going to be infinity or negative infinity. But as you plug in values slightly bigger than 1, it'll be like, say, 1.1 minus 1, that's going to be positive. So positive over positive, so that's going to be positive infinity. But then since these don't match, the limit in general does not exist. Okay, so that's kind of doing the same idea without the graph. All right, any questions on that? All right. Okay, so go ahead and try this. Find the limit as x approaches 2 from the right and x approaches 2 from the left of 1 over x minus 2 without graphing. All right, so Joey, what's the limit as x approaches 2 from the right?
Would it be positive infinity?
It would be. How about as x approaches 2 from the left?
Negative infinity.
Negative infinity. And so then what's the limit in general?
There isn't one.
There isn't one. It does not exist because the left and the right hand limits have to match. Okay. All right, any questions on that? Okay, so all the limit laws that we've learned before still work for x approaching infinity or x approaching negative infinity. Okay, so the variable x can approach a finite number or infinity, and all the limit laws that we've learned still work. You can add them, subtract them, multiply, divide them, raise them to a power, what have you. All right, so let's say we want to calculate this. Well, we've learned that when we're doing sums, we can do the limit of each one separate. So the limit of a constant function, that's just going to be 5. And so then as x approaches infinity, we have a constant over infinity, and so that's going to go to 0, and so the answer would be 5. So those limit laws still apply. All right? So see if you can do practice 2. All right, so Chloe, when you've got it.
I'm a little bit lost. Would you do the top and the bottom separately?
Sure.
Is that how you find
I
it?
would. I would.
Okay.
So, but see, because the top, there's no x to plug in. So
Okay.
what would you get on the top?
0?
No. If there's nothing to plug in, it's just a constant. So it would be that thing. So it's
so
just pi,
it'd be pi.
pi
okay.
radical 3.
So then you just have to find the bottom,
Yes.
which would be positive infinity?
Yes.
Okay.
So when you have a constant over infinity, what will that go to?
I don't know.
See, think about like a denominator that's getting bigger and bigger. So like, let's say you had 5 over 100, 5 over 1,000, 5 over 1,000,000, 5 over 1,000,000,000. As the denominator's getting bigger and bigger, what's happening to the whole fraction?
Getting smaller?
Yes. And so it will approach what?
0?
0. So anytime you have a constant over infinity, it's going to go to 0. All right, any questions on that one? All right. Okay, the limits of infinity at rational functions. All right, so it says to determine the limit of a rational function as x approaches positive or negative infinity, we first divide the numerator and the denominator by the highest power of x in the denominator. Okay, so let's see what that looks like. All right, so here we're taking the limit as x approaches infinity. So if we just plugged in infinity and you have any power of x, you're going to get infinity. So infinity over infinity. So that's not good enough. So that's what we call an indeterminate form. So if we divide by the highest power of x in the denominator, that would be x squared. So we're going to divide everything by x squared. So then what that's going to simplify to is this, because the x squareds will cancel, so we just have 5. And then 8 over x minus 3 over x squared. Here the x squareds will cancel, so I'll get 3 plus 2 over x squared. Now, each time we have a constant over infinity, that term is going to go to 0. So this ends up being 5 plus 0 minus 0 over 3 plus 0. And so then that would simplify to just 5/3. Okay? So you divide by the highest power of x in the denominator, then take your limit term by term. All right? So see if you can do practice 3. I'll leave this example up. All right, so Nathan, when you've got it.
Yeah. 0 over 2?
So 0 over 2 would simplify to what?
0.
0. Okay? So divide everything by x cubed, and then when you plug in, you get 0 over 2, which is 0. Okay? Any questions on that? Anyone like me to work it through? Okay. All right.
I
What's
have a
that?
question. Would it make a difference if it's 0? I mean, negative infinity, or is it all just 0 if it's like a constant number?
No, not for that. If it's a constant over infinity or negative infinity, it'll go to 0.
Okay.
Okay? All right, great question. All right, so next, horizontal asymptotes. A line y equals b is a horizontal asymptote of the graph of the function y equals f of x if either the limit as x approaches infinity of the function is b, or if the limit of the function as x approaches negative infinity is b. Okay? Now, one of the things that's going to help us is if we recall the idea of a horizontal asymptote in pre-calculus. Okay? In pre-calculus, when we're trying to find a horizontal asymptote, what we would do is compare the powers. So you have both the numerator and the denominator in descending order. And then you compare the powers. If the powers are the same, then the horizontal asymptote is y equals the ratio of the leading coefficients. If the denominator is, if if m is less than n, so in other words, if the denominator wins, then the horizontal asymptote is y equals 0 when you're comparing the powers. If m is greater than n, then there is no horizontal asymptote. Instead, there's a slant or oblique asymptote. And it says stay tuned because we'll learn how to, we'll remind you how to do that. Okay, you do that in pre-calculus as well. So this is actually a slide from my pre-calculus class. But the thing is if we remember this can actually help us when we're doing calculus, because a horizontal asymptote is really a shortcut for finding the limit as x approaches plus or minus infinity. If we can just do this, then we don't have to do all that dividing by the powers all the time. All right, so if a function approaches infinity as x approaches a number from one side and negative infinity as it approaches from the other side, we say the limit does not exist. Let's see, that's not on your paper, is it? So, and we've done those before, is where the limits at infinity have to be the same. All right, now, so probably where we're gonna, I don't know if we'll be able to finish both the example and the practice that have to deal with absolute values. But this is sort of an added little trick that we don't really talk about too much in pre-cal, is that absolute values are hard to do calculus on. So a lot of times what we'll do is determine if x is greater than or equal to 0, then we'll just drop the absolute value signs, and then we can do calculus. If x is less than 0, then we'll drop the absolute value signs and change it to the opposite of x. So this is a little trick to get rid of the absolute values. All right? Because, see, like, let's say here we want to compare the exponents. So what we do is we say, well, if x is greater than or equal to 0, then that means I can just drop the absolute value, okay? Because as it is, we can't, but when you look, okay, x is positive, so you're allowed to just drop it. Okay, so now that we've got rid of that, then we compare the powers. So just like when we're finding the horizontal asymptote in pre-calculus, if the powers tie, the ratio is 1/1, the leading coefficients. So the horizontal asymptote is y equals 1, and that's exactly what the limit is. So y equals 1 is the horizontal asymptote, and 1 is the limit. Okay? All right, so see if you can do practice 4. And if we don't have time to talk about it, well, that's where we'll start tomorrow. All right, so Rachel, if you get the answer before we drop, call it out. Otherwise, we'll start there tomorrow.